Okay, hi everybody. Thanks for coming. So today is our final seminar of the ESRG seminar series. So yeah, thank you very much for coming this semester. We've had a really good turnout and I hope you've enjoyed it. We're in the stages of planning the seminar series for next year. So if you have any suggestions of speakers, that would be much appreciated. I'll add in the spreadsheet in the chat momentarily. And also, if you're interested in joining the seminar organizing team, or if you have PhD students that might be interested, that would also be very welcome. So now I'll hand over to Leo, who's going to introduce our final speaker.
All right, hi everyone. So it's my pleasure to introduce Florian Wellmann. Florian is a professor in computational geoscience and reservoir engineering at RWTH. I always have a hard time with that one. RWTH Aachen University. He studied geology with a focus on applied geology and geophysics at Tübingen University. After that, he had a stay on the Antarctica research station Neumayer 2. And that's the German station, is it?
Yep.
Awesome. Right. So afterwards, Florian started his work on geological modeling with uncertainty quantification for geothermal resource estimations at the Institute for Geothermal Resource Management in Mainz. He followed by PhD studies at the University of Western Australia in Perth on the same topic. After he did a postdoc positions at CSIRO and CET in Perth. So after that, Florian obtained a position as a junior professor at RWTH Aachen and was promoted to full professor in 2018. He also has extensive experience in geological modeling, geophysical process simulations, joint inversions, and uncertainty quantifications. So I'm really looking forward to hearing what he has to say about all of those topics. And I'll hand it over to you, Florian.
Thanks a lot. Thanks a lot for the invitation to speak here. Great to see also familiar names and faces here. It's really a nice chance. Thanks for the invitation. I'm going to swap to my screen share. Let me just set this up in for a second here. I hope you can all see that and stop my video here. And just make sure that I can see the chat in case there's a question already in here. And I guess get started. So can you see my screen? It's all fine? Okay, perfect. So thanks a lot for joining today. It's a special day, end of June, and for other reasons. Let's actually go ahead before we go into geologic modeling. I would take a bit of a different perspective to start with. And this is looking at Pluto, and you may wonder why Pluto. Well, this is the way that we saw Pluto. This, what used to be a planet, it's been degraded a bit, but something very far away, of course, 30 astronomical units away from Earth, until there was this mission by NASA, which flew closer, and we suddenly saw something very different. Until, well, this is what probably all you have in mind right now, but that's not what I'm talking about here today. I don't know what this is, this ball, and what football means. So let's go ahead. What we actually saw afterwards, after this mission, is this incredible picture here of Pluto. And it always amazes me to think of the fact that we have such a high precision knowledge, basically, of a planet, or this astronomical body, which is such a huge distance away from us, that you can see craters and all these little details, and we actually barely know what is happening just 1,000 meters below our feet. And that's the topic of my talk, in a sense. So what I'm going to present you today are methods around the topic of probabilistic machine learning for improved decision-making with 3D geological models. And in the essence, basically, as a summary, if you want to have this at the beginning, basically is the outline. How can we best combine information to learn something to better see basically into the subsurface? Before we start to talk about probabilistic machine learning and decision making, let's first go a little bit take a look at 3D geological models first and what we mean by there. So in this talk, I'm going to give a bit of an overview of geological modeling concepts, going to talk about uncertainties in geological models, and then swap a bit to this idea of probabilistic machine learning and this viewpoint of how we can integrate data and knowledge, with a bit of some case studies, and if we have some time, also some notes on implementation, software, and further use there. So what is 3D geological modeling? Well, 3D geological models are routinely constructed for a wide range of topics and applications. I have here one study which was done just in my neighborhood here near Aachen by a student of us, who worked on a model for a fold and thrust belt to better understand potential settings for geothermal systems. And what he did is he combined a lot of information, as we commonly do then, from geological maps, some drill holes maybe, to obtain 3D pictures of structures. And, you know, it's really complicated. So let's look at a cross section. We can see here these the thrust inside, and we can see this fold belt. So this is a very complex structure at depth, and we see this. We can visualize this as very high precision. You can generate nice movies out of that if you like. But of course, the question is always based on the fact that we have to combine a lot of different aspects of data, of knowledge into these models. How accurate are these models actually? And this is something that has been bothering me for basically all of my research life. When I started constructing these models for geothermal studies and gave them to reservoir engineers or to people who did simulations on them, and realized that they take these models sometimes as basically as the truth. And it's very difficult to convey that actually, in fact, sometimes we don't really know that much. So what are the methods for geological modeling? This is just a very quick review here in a sense. Consider that we look at a cross section somewhere through the earth, and we could say that we have here some sort of a layer offset maybe by a fault. And if you have this picture in mind, quite commonly we think of large-scale structures, like we have here a picture of the Allgäu in the Alps. If we go closer into some of these layers, we could look at things like maybe sedimentary features, channels, and so on. So this is typically happening on a smaller scale of meters to tens of meters maybe. And if you go very close, if you zoom into these systems, then we look at heterogeneities, very small scale variability. That is basically, as in this case here, distribution of grains or pores in a rock. Why is this important? Well, because actually on each of these scales, we have different types of models that have been mathematical models that have been used to describe these types of geological features. So at the smallest scale, this is something where the field of two-point geostatistics has been very successful. And again, we have to point out here, the scale is just an approximation. Also, these methods can be used and have been used also on larger scales, but always with this idea of these random heterogeneities. On this level of channels, there are methods like multiple point geostatistics or object modeling. And if we look at these large scale structures, in a sense, these interfaces, we typically talk about methods from structural modeling, or sometimes it's called trend modeling. So this is the topic of my talk today. Let's look a bit more into what we mean there. Again, look at some, if you have a picture of a mountain bed in mind, this is typically the right picture in a sense. Or, I mean, what we typically show in geological maps as well is the same type of consideration. And why do we do that? Well, because we can actually describe many aspects of geological history, so things which evolved over a long time scale. And we had sudden changes, and then these changes actually quite often today visible in discrete surfaces in time, in a sense. And so we have things like faults, in this case is thrust faults here, or we have changes in maybe sedimentation, background sedimentation or something, which led to distinctively different sedimentation style and sedimented properties. And this is, of course, this always happened over a certain time span, but as we look at it today, it appears to be a sudden change in properties, and this is quite often, in a sense, seen in discrete interfaces. This can also be on many scales. Important is that what we consider here, that these interfaces basically also lead to deposition or the presence today of different types of rock properties, something which also leads to distinctively different geophysical signals or geophysical properties. So we can also see this using things like seismic data and so on. And then we can use this actually to encapsulate all these aspects of geologic history in these types of boundary or surface-based modeling methods. So how do we actually now, how can we draw, how can we describe these interfaces and surfaces with a mathematical, in a mathematical form? This is something which has been an active field in research for, 40 or 50 years as well. But I'd just like to point out two different methods and to show how they work. I think it's nice to look at the example of a circle. And that's something, of course, which we all know still from high school or undergrad maths maybe. Questions of how we can describe a circle with a mathematical formulation. And there are basically two basic concepts. There are many ways in which we can do it, but there are two basic concepts. The first thing that we need to do if we want to describe the circle with a mathematical equation is that we should describe some sort of a coordinate system. And then we can use one method, which is fairly straightforward. We can describe, we can realize that each point on the circle, I should go over here, can be described by an xy coordinate, which is related to the trigonometric functions cosine and sine. And we can define a so-called parametric description as a point t, which basically moves on this circle by describing x as the cosine of t and y as the sine of t. That's a so-called parametric description where we use basically one variable t, for example, to describe all points on this circle. I actually think that probably when you thought about this, how to describe this circle, you actually had another representation in mind. And this is what is also sometimes called the circle equation, which is actually describing the circle as all points which are a certain distance away from the center, as x squared plus y squared equals r squared. So we use the Pythagorean triangle concept basically to describe all points. And when we do that, actually, we describe the circle in some sense as a line, as a set of points in a field, right? This is the field here shown. I don't have the color bar, but it's increasing from 0 to higher values up here. And equal colors correspond to equal sets of points. And then the circle is actually one set of points in this field. And we can think of this also in 3D, that we basically have here, we can draw this shape here of this bowl shape in a sense. And then the circle corresponds to a cut through this bowl in a sense, at a certain position here, position 1, which corresponds to our radius squared actually. Okay, so this representation is something which is fairly common when you look at curves. But you can also use the same idea actually in one dimension higher. And this is a so-called implicit representation of geometry. So you can use the same idea to also display and calculate, first of all, calculate and show surfaces in 3D space. And what we are using in our work here is a method implemented in a software called GemPy, one of our developments, where we combine different geological input data types, typical surface point, so points on the surface, and orientation values. And we calculate from this information this three-dimensional field, and this gives us then by extraction, in a sense, these 2D surface representations. I heard this picture may be a bit not so smooth over this movie here over Zoom. But what you hopefully see is that we can change points, and while we're changing points, this entire field is reconstructed. The surfaces are extracted with a contouring algorithm, and this gives us our representation of geology in three-dimensional space. Okay, so we have this implicit surface representation method to show geology. Now let's see what we can learn about uncertainties in these models. When we go through the classical conventional workflow of geological model construction, we actually go through a quite a set of steps. Typically at the beginning, you may look at a region and decide, first of all, what kind of geometric features am I going to expect here? Is it a nice sedimentary basin setting where I assume conformal sequences, or do I have faults that I have to consider? Do I have complex dome structures or metamorphic domains? And all of these decisions, in some sense, considerations lead to a decision on a certain type of modeling method that you're going to use. Once you decide on some sort of a modeling method, for example, the one I've shown with these implicit fields, you need to define the structure of the underlying mathematical model. For example, how many interfaces do you want to show? How many features are relevant? To what level of detail do you actually go? Once you decide this structure of the mathematical model, you need to parameterize this model typically, where this is actually always the case. There's never a default setting that would work in all cases. So you need to decide on some sort of parameters of your model, for example, weighting parameters, or if you use, for example, kriging methods, geostatistical approaches, you have to decide on the parameters of your kernels and so on. And finally, you need to, of course, look at your input data that you use for your interpolation. This is always also the case that you cannot simply take all your input points and dump them into an algorithm and expect to get a perfect model out. This is always a lot of data preparation beforehand. And of course, these points themselves may also be uncertain. So you may not know exactly where they are. And all of these aspects lead to potential uncertainties in your final constructed geological model. So what do we actually talk about when we talk about these uncertainties? That's something which there have been, in the meantime, a couple of studies investigating geological uncertainties. This is still one of my favorite ones from Gabi Couriot from BRGM, which has been performed already, as you can see here, already 2012, presented in Brisbane. Because what they've done is actually, so this is the team behind GeoModeler, also a really well-known geological modeling software. What they have done is actually, they've done a mapping campaign in the same region in southern France, a mapping course for students, master and postgrad students, for more than 10 years. And kind of special in this, in their approach was that they always did mapping and modeling at the same time. So they always created full 3D geological model for the same region. And they now have a fantastic set of, I think in the meantime, 15 or 16 geological models for the same region, constructed for the same region. So what they've done now, after some years, let's take here a section through these models, and it's actually, they thought, let's see how these models actually differ that were constructed over all of these years. So what we can see here is one cross-section. All these models are in 3D. And you can see one geological interface here, one contact and one fault from the first model. And now we're going to add more realizations. Okay, the beginning still looks kind of like the initial model, not too much variation. Oh, but suddenly here the fault is tipping in a different direction. Interesting. Over here now we see some variability evolving in these interfaces. Suddenly now there's a new fault appearing on all the way on the right side. And we see a huge variability in the expected dip of these faults. So over here we can see, they're all the way from vertical to dipping in one direction, and the other one we can see here is quite a scattering of maybe 45 degrees of these faults. So this is, in some sense, you can consider this as mapped uncertainty. This is, in some sense, the result of many studies over many years in the same region by different people, where all aspects of model building come together. I mean, even things like, conditions in the field, people finding the nice outcrop or not, some additional information or concepts that the students may have had or may not have had. So they had all, in a sense, many decisions were already taken for them, like the type of modeling method they were using and so on. And still we can see that we would get very different geological models for this region. So in some sense, this is what we have to deal with. The problem is now, in reality, of course, we cannot simply go and model and map the same region for 100 times each time when we want to create a model. So what can we do instead? And one possibility that emerged also over the last 10 years in a lot of work was the idea to use stochastic modeling methods. How does this work? In sense, instead of taking all of our input data points and orientation measurements as perfect, we try to assign meaningful uncertainties to these input points and parameters. And then we actually, instead of creating one model based on these defined uncertainties, we create a range of input data sets and different model realizations. So here's an important step in this geological modeling concept. I mean, these methods are well known from geostatistics and also now from machine learning in a wide sense. But to say that we treat the model not as a deterministic, perfect model, but we assume that there are uncertainties in this model. And this is something which has been established now, and many studies are using these types of approaches. The question is, however, I mean, what do we get out? We get something out where we see now, instead of having one interface, we actually do get multiple interfaces here. These red lines, the faults are considered as fixed, but we can see that we have a variability around these layers. So that's fine. But the big question that we have to ask ourselves is if actually this, I mean, it looks a bit like what we observe in reality, but is it actually really comparable? And what is the problem? Well, of course, we do this here, the stochastic modeling approach, on the basis of idealized settings for uncertainties. We assume that we have knowledge about these distributions. We assume that the some parts of the model are fine as they are. Whereas in reality here, we get all of these different uncertainties coming together that finally lead to this representation of uncertainty here. So we wanted to understand if these methods are actually working or not. And what we did is we looked actually at this entire process again and first tried to distinguish different types of uncertainties. This is here a really nice diagram from a student of ours, from Elisa. She has this nice block diagram, and in a sense, asks the question, assume that you have some sort of this is the surface, you're walking around here as a mapping geologist. You may find, one rock type on one side, one on the other side, and in between you don't find anything. There has to be something, there has to be somewhere, there has to be an interface maybe, but where is it? And you could say the first geologist is coming along and she says, well, actually, I think this is a fault. I see a similar setting a bit in the vicinity of a normal faulting, and this would explain this difference in my rock types that I observe at the surface. A second geologist may come along and say, I agree, but actually the fault is not dipping 60 degrees, maybe it's more like 45 degrees. And then maybe there's another geologist coming along with a background in sedimentology, a strong background in sedimentology maybe, and thinking, well, this looks really like coarsening upward sequences, fits to this rock type that I observe here. So I assume that there's maybe not a really distinct boundary, maybe it's just a coarsening upward sequence. This is, of course, highly idealized or simplified. In reality, you have a lot more information. The important point is that we have two very different types of uncertainties here. The first one is actually, first of all, we can consider all of these uncertainties as epistemic. We can say they are all due to a lack of knowledge. If we would know more, if we would drill down in each location, if we would take detailed sedimentary studies and detailed tectonic studies, we could resolve maybe all of these uncertainties. But they're different in a sense because we can classify the first ones as basically two realizations of a similar type of uncertainty. And this is about the exact position of this interface in between. So we can actually group basically some sorts of uncertainties into aleatory uncertainties. So these are uncertainties that we can describe then with distributions and use them in our stochastic modeling approaches. But of course, this other uncertainty is very difficult to include in these automated modeling methods. Some approaches exist, but let's stick to these ones here at the beginning first. So how do we capture now? Do we actually capture this range of uncertainty? As I said, there are so many aspects coming together when we talk about uncertainties in modeling and mapping and so on. In the end, there's one aspect that is always there if we talk about geological studies, and this is this aspect that in geology, it's very difficult to separate knowledge from observations from knowledge. This has been something which has been very nicely described in this paper by Wellmann, 1995, who described geology as a hermeneutic science, where basically always these aspects of knowledge that you as the geologist bring into the field with you already, that this also distinguishes somehow what you can observe and what you can see. And this is difficult. So we see that we have to deal with all of these types of uncertainties. And so the big question is, if we now try to mimic the uncertainties in reality with our stochastic approaches. Do we get close to what we would observe in nature? So it's difficult to estimate. So we actually went back to Alès, to this region where this study was performed before, and actually joined one of these mapping classes and did a very detailed study on uncertainties in all the data that was collected. So to give you a picture of uncertainties in the field, I mean, that's something which all of you know as geologists. Sometimes you have perfect conditions almost. You have a nice outcrop, you have nice consistently dipping layers. Then you could say, if I take repeated measurements there, they would all look more or less the same. Of course, it gets quickly different when you look at maybe some bit more difficult outcrop conditions, all the way to cases where you have to estimate more or less the orientation of your layers and structures, when the variability of repeated measurements would be very high. So what we've done basically is doing all of these whenever we took a measurement there, trying to take not one measurement, but many repeated measurements to estimate the distribution around our measurement points. Now, the same for another aspect of uncertainty, which would be the location of a geological feature. Assume that, in this case here, this is a valley structure, but let's say we have outcrops on both sides of this valley. Then we can, like in this case of before that I showed, we can estimate that in between somewhere we have to have this boundary, but we don't know where this is really. And so we can assign a range of uncertainty around this position. And we've done all these things in a very careful and detailed way and used this now as an input to this stochastic modeling engine in GemPy, so that we generate, instead of just one model, a whole set of different types of models. What does it look like? A quick introduction, and first, before we go into the results and how we can visualize that, there are basically, the topic of how to visualize uncertainties in 3D is in itself a super interesting and not so easy topic. One intuitive way, at least in a section, is to say that we can basically stack results like what we've seen before. So we can visualize realizations on top of each other. Here you see this is the uncertainty only of the position, and here we have the uncertainty also of a dip of our interface. What we've been using for quite a while is now also entropy as a measure of uncertainty. What does this show here on the right-hand side? In each cell, basically, we calculate the probabilities for all classes of outcomes. So you can think of different rock types, let's say, or lithologies. And then we, from this distribution, we calculate the entropy, and this gives us a measure of uncertainty in each cell. And we can see this up here. This is showing that we have a high uncertainty in this range where we have this uncertainty of the position. And it's a bit different down here where we have basically this fanning out effect of dipping uncertainty at the top of this feature at the top up here. We can see that uncertainties are increasing to depth. So let's see what this looks like in the case of these models that we looked at before. Here's the calculation of entropy. If you have questions about that, I'm happy to talk about this topic as well, maybe a bit later. So what does it look like in reality now? This is why you can already see why we maybe look at entropy, because it's quite difficult to look at these plots up here. It's really a bit of spaghetti lines here on the left side. But let's look what we have up here. So these on the left and the upper side, the upper frame here are these manual, we call them manual models, but these are the models that were generated by these multiple generations of geologists in the field. And you can see this variability. So this is, I think this is the cross-section that we saw before. And there are some other cross-sections through this model. And we see this variability of the mapped models in a sense. Down here, we see these stochastic realizations that we artificially generated. And we do see that we also have a variability. It's not quite as extreme as up here. Let's look at the entropy as a comparison. And if you look at these cross-sections, we can see that at least for some of these layers, what we see is that at least the variability in our models reflects this variability in these mapped uncertainties in a sense, in some regions. But in other regions, we can see that there is a huge strong dependence on the initial model. And that's something which is a bit expected on the way that we define these uncertainties here, because we start with a distribution which has then logically some sort of a mode or mean in this case here, if we look for a position uncertainty. And so we already bias basically our model by our best guess. So that's something which maybe could be improved by using multiple experts at the beginning, but still a big point to keep in mind. So this is was a bit of a look at uncertainties in geological models. And what I wanted to show mostly is that these stochastic methods, well, they exist now, have been used in a wide variety of different settings. But a big but to always keep in mind is that, of course, all these estimates of uncertainty that we get are also models of uncertainty, which are biased in a sense by also the geologists and the modelers who perform the study, just like a normal model in a sense. But they give us at least an estimate of variability. Okay, so what is the problem with these stochastic forward models? And one thing that we also have to keep in mind, what could possibly go wrong when we do these studies? Well, there's one problem which I did not mention yet, and this is if you take your input points, let's say, and we now start to randomly perturb these points, that what we expect to happen is somehow that we may get a new distribution of points, which lead to a different dip maybe in here of this layer of the fault, but it still looks something which looks at least similar to this first realization with some sort of variability. But what could happen is that suddenly one of these points here, they are completely swapped, they are moved around, and suddenly you get to something which would lead to a complete failure in your model construction, depending on the algorithm you would be using. And that's something which everybody who has been doing some modeling with geologic modeling methods knows, that suddenly you may get models with some blobs somewhere, really strange behavior, which does not make any geological sense anymore. And typically this is because you're somehow violating the assumptions in the underlying model. Another option that could happen maybe is that suddenly these points of our fault are completely going in the opposite direction, and suddenly we would have a fault that's dipping in the opposite direction. And in this case, this could lead to some sort of a failure of a geological constraints, we could say. So suddenly we get to something which used to be a normal fault before, to maybe a thrust or reverse fault, and this could be violating our idea of the geological history in this region. So why does this happen? Well, of course, when we auto-generate these models, then this is done in an algorithm in the computer. So clearly, what can happen here is that we're not respecting correct parameter correlations. If you would show these models to a geologist, you could directly say, this doesn't make any sense. This is not fitting to the tectonic setting or something. But this workflow, the automatic workflow, is lacking this knowledge. And so a question that has been bothering us for many years is, how can we include all these aspects of knowledge back into these geological modeling engines, in a sense, and these stochastic modeling engines, to obtain models that are, at least on average, more realistic. And this is now the next topic I'm going to talk about here, in this concept of probabilistic machine learning. So what is probabilistic machine learning? Here's an excellent book with the same title, Probabilistic Machine Learning Introduction by Kevin Murphy. The second edition just came out, or will come out in a couple of days, I think. It's already accessible on the website as a preprint, I think, from Kevin Murphy. So it's really, if you want to delve into this topic, a fantastic book, I think. He has here a nice comment, or a nice definition from Mitchell from already 1997. What is machine learning? Well, in some sense, it's a computer program which is supposed to learn from some sort of experience E with respect to some class of tasks T and performance measures P. So we have these three aspects coming together. We have a program, so some sort of a forward model, in a sense, a computer program, which should improve by experience with respect to some performance metric. If we look at probabilistic machine learning now, then the essential point is that we make a step to decide that we do not take parameters as deterministic values, but we assume that they have some sort of an uncertainty. And we apply this idea to basically all the unknown quantities in our system that we're evaluating. And we describe uncertainties using probability distributions. And even though there are other ideas around how you could describe uncertainties, this is a system which is consistent with many underlying basic considerations of how uncertainties behave. The question is, how can we apply these concepts to geological modeling? And that's what I want to talk about in the next couple of minutes. Well, the idea is actually, first of all, we realized we may generate models that may make no geological sense. So somehow we need to find ways, we need to find these performance metrics in a sense to say, or performance measures to say this model makes sense or this makes more sense than this model maybe. Then, of course, we need to describe our parameters as random variables. And we need to, in the end, find ways to then learn from these performance measures. So we need to estimate parameter distributions and correlations that make most sense in a sense. And you want to quantify uncertainties in these models. And this basically together brings us to the realization that we should consider geological modeling itself as a probabilistic machine learning problem. And of course, the person that maybe turns up here in our picture when we talk about these things is Thomas Bayes, the English reverend who came up with this idea of what we now call Bayesian statistics to have a prior that we update by knowledge. And this is encapsulated in this, what we now call the Bayes equation, although it was later described by Laplace in this form. But in this conceptual form, this is what we think of here. And let's look at what this means in the context of geological modeling. We have some sort of set of model parameters beta, and we may have some prior knowledge about these parameters. This is, for example, from repeated measurements at a position, or even from expert knowledge if you don't have anything else. Then we have data. This is over here, so additional observations. And what we do is we define likelihood functions here, and these likelihood functions describe how likely, this is now something which is important to realize here, likelihood functions are likelihoods of the parameters. So how likely is a parameter given this observation in our data set? And this, if we combine this and we have to normalize it by this so-called evidence here in the denominator. And if we combine this together, we obtain the posterior distribution over our parameters given this additional geological knowledge. In a conceptual view, we can also describe this nicely in the form of a diagram. I have over here this example of a so-called Bayesian network, but where we have basically these prior parameters are our betas, and we combine these prior parameters with our additional observations. Inside here, in these arrows that I have here that look so harmless, this is actually where we have a lot of the difficulties later on in how we combine this information. In the simplest case, you can think of these arrows as being the likelihood functions in a classical Bayesian sense as a conjugate prior, for example. Let me give you one simple example. Assume that you have maybe here 2 layers. So let's say we have a 2-layer system, and it's a 1D approximation. So we say that we assume that we have 2 layers at depth of interest, maybe 2 top of sediment sequences. The upper one we assume to be less uncertain than the lower one. But let's say that we have an additional information. So we describe this by distribution. So we say this is here the distribution describing our top of sediment 2. This is top of sediment 1. Now let's say we have some sort of an additional information from maybe observations in the vicinity that these layers in between here, so between top sediment 1 and 2, that this is always expected to be in the range of maybe 180 meters plus minus here distribution around this point. So what we can do is we can sample now from these sequences here. We can generate realizations, and then we want to only keep these realizations that fit, at least on the long run, this distribution of thickness that we obtained before as a likelihood function. And if we do that, we can combine this knowledge. Basically, we can obtain now updated estimates about the position of these layers at depth. First of all, we realize this will reduce uncertainty about this lower layer because we combine this information clearly. And secondly, we also see that from adding this information about the layer thickness, we actually get from 2 parameters that may have been at the beginning may have been independent. You can see this here, the joint distribution. There is no correlation obvious. We obtain something which is highly correlated as a distribution. And what does this mean? Once you have learned this distribution, if you would now take a sample from this distribution and generate one of these models with these updated distributions and correlations, we would automatically obtain models that also fulfill this criterion here. So we learned something, we basically updated our system in a sense. So we learned from this additional aspects of knowledge, and we updated our distributions and obtained now a system that leads to a more consistent modeling. So this is all nice in a simple case, but how does this look like when we now add more complex geological modeling methods? And this is where, of course, now all the tricky parts come in. First of all, we need to realize that we need to add some sort of deterministic function in between our parameters and our model. And these functions can take multiple forms. Most famous, this is actually also from the field of geophysical forward simulations, but also our geological modeling method can be considered as a deterministic function that we place in between into our probabilistic modeling workflow. And if we do that here, we can describe now transfer functions in a sense. So we can describe geological modeling as a deterministic function in this branch here. And we can add on top other types of deterministic functions, like, for example, gravity calculation. Why? Well, of course, if we have an input data set of our betas, let's say our positions of our interfaces and faults, then we first need to construct this geological model, use it as a basis to calculate then gravity. And we can then compare the predicted gravity to the observed one in reality. How does this look like? Let me actually just quickly skip forward a bit in the interest of time here. Just would like to show you one example of a study in Australia, in the sandstone greenstone belt. Let me just skip forward directly to the model. What does it look like? We did something similar to what I've shown before in the case of ALES. So we went basically and carefully constructed models and assigned uncertainties to our input points. You can see here on the right side again, one 3D realization. On the left side, we can see these interface points and uncertainties. So in the first step, we do something similar to what we've done before in ALES. We only look at uncertainties in these model parameters and the effect onto our geomodel. So we look at this upper part of our branch here. And again, we see here a visualization of entropy as a measure of uncertainty in 3D space. Now let's look at this actually in a bit more of detail here and some more results. We can see that up here, this is a cross-section taken from one of the ensembles of generated models similar to before. We can see now here also a forward model gravity field, which would correspond to this model. And we can see the difference between this forward model gravity field and the measured gravity values. And we see here a 3D representation of uncertainty using entropy. So now we went ahead and we see in this case here we have a mismatch in the geological model and also in the geophysical calculations. So what we've done is actually we looked now at geophysical data, at gravity in this case here. And similar to what we've done with the geology before, now we define a performance metric in a sense on how our forward modeled gravity fits to the observed gravity. Of course, something which in the context of geophysics we call geophysical inversion. Here it's based on our model. And this means that we actually extend this branch here from our model parameters over our geomodel and a transfer function to the observed measure of gravity down here. What does this look like now in our results? Well, we see actually that now we get something where we see, first of all, down here, it's maybe interesting, we see a better fit to gravity, to the observed gravity. That's something which we would expect, right? If we use this additional information, it should be considered here. We see that we now get some significant problems in the geological model, and I don't have time to go into detail here, but what we see in this study is actually that now suddenly we get models that when we showed them to the geologists who did the modeling in this region set, doesn't make any sense. You're missing now many of the geological constraints. But we see that overall down here, the uncertainty is reduced. We have now many regions, like in this part over here, where basically a lot of uncertainty that we had before now is reduced. But what bothered us, of course, is this aspect of geological knowledge up here. So we went back and talked to the geologist and asked, so how would you describe now what is geologically realistic and what is not? And that's sometimes difficult to encapsulate. We actually managed to extract, in a sense, 3 types of performance metrics for this geological model. One is based on expected or unexpected unconformities, and another one about the type of folding pattern. Not going into detail here, But we included all of these measures into our modeling framework. And basically what we did is on top of this geomodeling branch here, we added a second type of observations in our probabilistic framework here to only keep models that kind of fulfill this criterion in the range of uncertainties. And what we obtained then are models now here on this right-hand side, where now interestingly, this is in the top picture, you see this is now, we have now this nicely, this double folding pattern in here. We have a nice continuity of interfaces. So that's something where the geologist said, okay, this looks acceptable now. But interestingly, the match to gravity also is still fine. But we see that actually the uncertainty, the overall uncertainty in this model increased again. And that was very interesting when we looked into this, because we have now, in some sense, we added information, but we end up with higher uncertainty. And where does this come from? Well, of course, we have some sort of a conflicting information in some parts. All of our aspects of the initial model itself, the definition of how this model is used, maybe even in the gravity forward model and definition of densities and so on. We still have many uncertainties that we did not consider here. And this is something which is obvious when we combine all of this information, we see that we have some sort of a conflicting evidence at some points. Let me quickly, again, skip forward a little. Just go to the next slide here. I wanted to show you as an extension of what else we can do. We can also add additional types of constraints. So that's something we've been working on a bit more recently, and this is a nice case. That's why I wanted to show it here, because the paper just came out 2 days ago by Alexander Scharf, one of our former students. And this is using topology as a likelihood function. So basically, we can see here that we can use the relationship, the connection between different geological bodies. We can draw in topology graphs and use this as a way to decide if a geological model that we generate makes, in a sense, fits to our geological expectation or not. And that's something which we've done in this paper here in a nice study in the Gullfax field in the North Sea, where we can see here on the right-hand side the topology graph. And we defined a metric and also a sampling method to sample from reasonable graphs, in a sense, and see that we could reduce the uncertainty here in our geological models quite significantly in some ranges where we have uncertainty about the position of a fault. Okay. So I still have 1 or 2 slides about GEMPI, but I think I should probably finish, Leonardo, or what should we have?
Yeah, so I mean, we still have some time. So if you want to,
I would just like to show.
That's okay.
Okay, thanks. Would like to show you just 1 slide about GEMPI or 2 maybe. Because something which I completely skipped right now is the question of how we do all these things, and that's something which is, this is a talk about geology and a bit more these geological concepts. But a lot of these things have to be, well, are computationally quite demanding. And that's a problem, especially when you look at the common way to construct geological models. It's usually that you have some sort of a model engine, expensive program, which allows you to generate these models. And it's very difficult to implement these systems into efficient sampling frameworks. So one thing we've been working on also for quite some years now is to build an open source geological modeling package. This is called GEMPI in here. And something which maybe some of you have seen this already. If not, it's even for geological modeling, I think it's quite useful, even if it doesn't have a nice GUI. It's built on Python. But one point that is, I think, really important is that it's actually built on efficient machine learning libraries, because we always have in mind this idea that we want to integrate this in these probabilistic workflows. And why does this matter? Because a lot of the methods we are using here are quite demanding. Yeah, some more on this maybe collaboration part, but what I really wanted to mention is that it's built around these efficient machine learning libraries like Theano and TensorFlow. And this allows us to integrate GEMPI as this deterministic function into things like PyMC. If you know, this is a probabilistic modeling framework for Python. We're also working on something for TensorFlow probability, which is a similar method for TensorFlow. Pyro is something similar for PyTorch. And based on this implementation, it allows us actually now to use geological modeling as one brick, in a sense, at one block in these complex sampling schemes for these probabilistic machine learning approaches. And this is really exciting. I think this is something which is really very nice and allows to do some things that have not been possible a couple of years ago. And one reason also is why this works is because GEMPI is not in itself, it's standing on a lot of shoulders in a sense, like many Python projects. This is a nice picture which was done a while ago by some researchers, I think from the SIMPAC team. This is a really nice representation of different modeling packages. I adjusted it a bit for geosciences. But of course, we have at the core, we have Python, then we have a set of very efficient libraries around it, more specific aspects like TensorFlow and PyTorch for these efficient computations. And on top of it, we have a lot of domain languages, packages right now, which allow us to combine different aspects from geosciences, geological modeling. We have geophysics here, Fatiando, of course, that is well known, I assume, in Liverpool. DeVito, other modeling packages for data treatment and so on. And based on this incredible network, in a sense, of or ecosystem of Python packages, it's really a great time to work in this field of computational geoscience right now. I think we can tackle problems that were just basically out of the reach until a couple of years ago. If you're interested, there's this very nice and active community on the Slack channel of Software Underground. If you simply Google for it, you'll find it, I'm sure. Okay. Summary, why GEMPI, why geological modeling, why 3D modeling? Well, I think this is something which needs not maybe too much explanation here in this round, but we use surface representations as a way to encapsulate geological knowledge. The problem is, though, that all of these models contain uncertainties, something which I hope I could show with this simple example at the beginning. But we now have a wide range of possibilities to consider these uncertainties. And one thing is specifically important, I think, when we look at these probabilistic machine learning approaches. I think one big step is to make this just mentally, this step from creating just one model to an ensemble of models, something which is already in the statistical community and machine learning as well, really widely done. It's possible in geosciences and geology as well now, and I think this is something which we at least all should consider. One statement which I think is super important is that the range of models that you generate in this ensemble, so the range of plausible models is never a plausible range of models. Nicely put by Grainiering and Hoshin Gupta here, they're researchers in the field of hydrology. What it means, of course, is that we can never say that we capture all uncertainty. The uncertainty that we include in these models and representations is also a model of uncertainties. It's never the truth. But we need to use efficient sampling methods, something which, as I said, I completely skipped in this talk. That's more from a mathematical perspective. But also there in this field of probabilistic machine learning, a whole range of very interesting methods are evolving right now. I think the fundamental geologically interesting questions are, what is the best way to combine geological knowledge and geophysical information? Always keeping in mind that we have this aspect, that geology always has this interpretive aspect. And I think as a geologist as well, this is something which we cannot and maybe do not want to avoid. But I think it's important to at least be aware of this and also express this when we are talking about our models and our hypotheses in a sense. Very next, well, as I said, this ecosystem of modeling and geology and geophysics is exploding right now. An amazing time to work on these topics, and yeah, let's see what is coming up in the next couple of years. I hope interesting things. Thanks for your attendance, and I wish you, at least for those of you who are watching football, fun the next 2 weeks. And of course, I'm happy for any questions right now.
All right, thank you for that, Florian. Virtual round of applause.
Thanks. Oh, I'm sorry, I took a bit too much of the time.
Oh, that's okay. It was a really interesting talk. So shall we hand it off to questions? If anyone has anything to ask, please feel free to unmute.
I certainly have to stop speaking. Yeah, David.
Hey, Florian, how are you?
Good, thanks. And you?
Yeah, it's good. It's good to see you.
Yeah.
That was really interesting. It's really cool to see all the stuff you've been doing with the modeling kind of summed up in that really nice presentation. So I quite enjoyed that. I just wanted to it's really interesting to talk about not just the uncertainty that we get with the modeling, but the uncertainty that comes with the data inputs.
Yeah.
And it was interesting. We were just in the field recently looking at some fractures in granites as a geothermal analog. And when you're measuring these things in the field, you go to your bias is to go to the outcrop that has the fractures in it and measure the fractures, but the outcrop over there might have no fractures. So you're already biasing your inputs by self-selecting sites in the field or wherever in terms of your data inputs. And we had an interesting discussion about it. And it made me think of Billy Andrews' paper. I don't know if you've seen that yet. They did some analysis on how different people actually approach things like fracture mapping, for example, and the different biases they bring with them to this study. It was very interesting. Yeah. And I just love to see some of that filtering its way into models. It's really, really cool.
Yeah, is this Aberdeen as well? Also
yes, yeah, Zoe.
Yes, yeah. No, that's super interesting. I saw that as well.
It was really cool, wasn't it? Yeah. But it's just amazing to see how some of this actually works in practice with the models. So I really, really enjoyed that. Thank you.
Oh, thanks. Great to hear. I mean, there is a lot to be done, as you say. I think what I really liked is this data set that we have from France, where all of these aspects, like, what do you see? What is the preference to go to which outcrop and so on? This is somehow, of course, still biased by really nice outcrops that you may have. But it somehow replicates a bit the fact that there are these uncertainties and decisions, and even things like weather conditions, or if you go to an outcrop when you are hungry or not. I mean, we all know that there is all these aspects of bias which are influencing us.
Absolutely, yeah.
And I think it's just important to also be aware of it.
I think that's like half the battle, is understanding that the understanding that you do have these variable biases in place when you go into the field, and you need to be aware of them so you're not letting them influence your data work as much as possible. But yeah, so cool.
Yeah.
I guess a quick question. Sorry to bogart everybody's time. I'm gonna have to go soon too. But in terms of putting this stuff into practice, have you seen much? Because obviously you've worked with geothermal quite a bit, and I've worked with geothermal reservoir engineers and modelers and stuff before. Have you seen much uptake or interest from the industry side of this in the application? Are they kind of like, oh, this is great, we need this for what we're doing industrially?
Yes, more and more, I have to say. I mean, as you know, of course, from Australia, it was, we did these studies there as well a bit.
Yeah.
It's been partly for the mining industry has been difficult. So we also did some of these studies with the mining industry in Australia, because they said we don't have a reporting code for uncertainties, so we cannot use it. Like, okay, well, does this mean you simply don't want to have them in a sense? It's very different in Europe. So we're working in some projects with the industry in Northern Europe, in Sweden. They're very interested in these aspects more and more, because they realize there's a value in it, not only but to get a better insight into where to maybe go and map or where to take more data, but just to understand what kind of uncertainties you may have in your systems. In geothermal, I see actually a lot of interest right now in Germany. There is quite a bit of a research. No, I mean, so there's no big new. There is now more development around geothermal again. I think is really great, and
that's good.
Yes, and so there is now, especially in this region around Aachen, this model I've shown before. This was really made to understand also the uncertainties for an expected drilling campaign. And I really like that, because we predict the uncertainties in this region where we are going to have a drilling in the next couple of months. So we can actually see our predictions, how much we are in the right ballpark, let's hope. And this is also linked more and more to simulations. So to use this as an input to simulations to see how these uncertainties affect also the geothermal simulations.
Well, that's going to be really interesting to see how that marries up and how well it works. Yeah, that's going to be really interesting.
And another big topic right now in Germany, I think it's the same, I guess, in the UK, is nuclear waste disposal.
Yeah.
And that's something where right now we see a lot of interest, because there is it's written in the law that that they have to provide an estimate of uncertainty in these models. And so this is not just something which is scientifically or maybe from a business perspective interesting, but there's a real obligation to show, at least to estimate some sort of an uncertainty in these models. And so I think this is really leading a bit to a cultural change, to say, well, this is our best case model, so accept it, to something where we say, okay, our estimate of uncertainty is also not perfect, but at least we try to show how uncertain we are.
Yeah, that's cool. That's going to be really interesting to see it all play out. Yeah, cool.
Yeah.
Interesting stuff coming up from you anyway. Yeah, great.
Thanks.
Thanks, Florian.
All right, thanks for that, Dave. Are there any other questions for Florian?
I have a question from the YouTube channel, if I can read that out. There are very positive comments and a question from Matthias, which is, can you model entities or objects, for example, lenses on top of and as opposed to stochastic random fields?
Yeah. So if I understand correctly, I guess you mean that if we have typically our interfaces and our bodies, that we would have some sedimentary structures inside, like channels and so on. That's something which is, we've been working on this. I'm not sure if I have a slide for this, but I mean, the big question is always, if you have some simple, like some nice layering, let's say sedimentary layering, you could include a random field inside, or also an object simulation inside. That's something which we've done. The question is, what happens if you have deformed bodies? And that's because you can assume that if you had some structures prior to your tectonic event, which may have led to a folding, then if you would calculate the distances in this deformed layer, let's say you have a fold, then the distance is following this fold, of course, and it's not just going straight across. And these so-called non-Euclidean distances, that's something which you can calculate. And then you can use this as an input to other types of object models. We call these hierarchical models. That's possible, yes. We haven't done it with object modeling in my research group, but it's certainly something which could be possible.
Thank you.
We also have Betty wants to ask a question.
Yes, hi Florian. I'm Betty, and I do a lot of work on microstructures and try and kind of extrapolate what I learned there to the big scale geology. And so your talk was incredibly interesting, and I was wondering, what is your sense for how easy or how quickly can machine learning methods that are developed or you're developing for large scale geology? How easy is it to transfer them downscale and vice versa? How can you go across scales? Because that's another big, I guess, big issue in our field. Scaling up and down is often tricky. Can machine learning help us there?
I think that's a super interesting question, of course, something which, especially this question around scales. And I mean, as you, of course, know, and I'm sure you have this also been in mind, I mean, there have been all these approaches doing this on the basis of classical physics-based models for many years, to some degree of success, I guess. We know, of course, from geology, we know that there has to be a relationship. It's just a question, how can we encapsulate this into our learning frameworks, whatever you'd like to describe. I think for machine learning, I mean, there is some interesting work in using machine learning methods for thin section analysis. We've also worked a bit in this field but mostly on actually generating input data sets, because it's very difficult to do for thin sections partly. We don't have, I mean, you cannot give a thin section to anyone in the street and say, identify the quartz and the feldspar grains inside, whereas you can do this for traffic lights, as we all know from these annoying captures. So there's a problem there in a sense, but of course on this level you could use conventional, in a sense, machine learning approaches like convolutional neural networks and maybe learn something about this behavior from many, many thin sections. But the more interesting question, I think this is what you are getting at, is how can we use this knowledge that we gain on these small scales to inform these models at a larger scale. And I think that many of the conventional machine learning approaches will not work there, because we simply don't have enough data. We don't have, we were limited in a sense by reality of what we have, and by the amount of data sets that we can generate. So all of these model-based approaches, what I've shown here is for the large scale, but I think that there are ways to combine also knowledge from smaller scales over models. So where we encapsulate knowledge, we hard code in a sense knowledge into these systems, but we have this knowledge. This is based on physical laws and so on. And the question is, how can we make this more efficient? And there is a super interesting field of research right now in these so-called physics-based machine learning methods, where you combine forward models in physics with machine learning approaches to speed them up in order to make these links more flexible and more data-driven, but also still based on this knowledge. And I think that's a super interesting approach.
Okay, great, thank you.
Yeah, thank you, Florian. Okay, so we're a little bit over time, so I guess we'll end here, and we'll transition into the Gather Town for some more discussion. And Caitlin put a link there, and we can continue chatting there. But yeah, thank you, Florian, for this wonderful presentation. It was super interesting talk and very inspirational use of virtual technology there.
Thanks a lot. Thanks for listening and for joining in here and for the questions. And I'll be in Gather in a second. Let me just go to my other room and grab a coffee. But I'll be there in a minute. See you. Bye. Bye, everyone on YouTube.
Bye. Thank you very much.